Okay, so let's do a little checkup here. Number one, in a short sentence, describe what it means to find a limit. So I want you to pause the video right here, and I want you to write down in your notes, in your words, what it means to find a limit. In my words, what it means to find a limit is you are analyzing what the function is doing and by the function, I mean you're focusing on the y values as you are approaching various x values. Now that's just in my words, okay? I want you to write down what's going to make sense in your mind, what's going to help you to remember so that when you're on the AP exam in May and they ask you about a limit, you automatically know in your mind what that means and what they're asking you to do. Secondly, let's look at a sample AP question. What is the limit of h of x equals x as x approaches pi? So what's the limit of the function x as x approaches pi? Now this is one of those things that they like to do. Sometimes they're going to phrase it in words. Sometimes it's going to be symbolic. You've got to be able to handle both. So here's the function. The function is x, and our x value is approaching pi. So go back to that theorem. When your function is x, the limit is always whatever x value you are approaching, which in this case would be c, which is pi. Okay? So that's one of those questions that not everybody's going to get right just because they phrase it in words instead of in symbolic form. So don't be thrown off if they say something in words instead of writing it out in mathematical symbols. Okay? All right, let's look at some other types of limits. We're going to find limits of functions that have problems. And I'm going to be a little cheesy right here and, throw in a little audio, maybe not. It's supposed to. There it goes. We're going to look at the limits of functions with quote-unquote problems. Now, those could be a variety of problems, maybe not 99 problems, but some problems. Yes, you can laugh at the corniness. All right, so problem type function number one, a piecewise function. Okay, piecewise functions. These tend to throw people for a loop, but they're really not that bad. Okay, again, if you think about them graphically, it's not that big of a deal. So our function is x plus 2 when x is not equal to 1. So everywhere except for x equals 1, our function looks like a y-intercept of 2, a slope of 1. So this is what our function looks like everywhere else, except at 1. And at 1, our function actually equals 5. Okay, so at 1, our function actually equals 5. Okay, but the question is, what's the limit as we approach 1 of this function? Let me tell you, the answer is not 5. That's the value of the function. F of 1 is 5. Okay, f of 1, you plug it into this piece, so your answer is 5. But if it's talking about the limit, think about it graphically. As we're approaching x equals 1, what are our y values approaching? Our y values are actually approaching that hole right there, which is 3. The answer for this limit problem is 3. Okay? You're actually going to plug it into, it's a little counterintuitive, you actually plug it into the quote-unquote not equal to piece, because that's the behavior of your entire function. The only time it equals that other value is at that one specific point. But we're talking about, well, where are we headed otherwise? Okay, let's look at another example. This one's got a parabola, x squared minus 4. when x is not equal to -3, x equals -4 when it is equal to -3. Again, let me just sketch it to get it in your mind what this looks like. A parabola x squared minus 4 means we have a y-intercept down here at -4. And try and make this as accurate as possible here. It's coming through. We're going to have a hole here at -3. Okay, that's a really bad parabola, but just ignore my art. Okay, and then it actually equals, let me use the same color. It actually equals -4 when the x value is -3. But again, that's not the question. The question is not, what is f of -3? That answer would be -4. The question is, what is our function doing? What y value are we headed towards? We are headed towards this y value up here, which is -3 squared minus 4, which is 9 minus 4, which is 5. Okay, this answer, this limit is 5. Okay, let's do one. This one I'm not going to draw it out. We're just going to run with it. Okay, just so, because I want you to get in the habit of just zoning in. When you see this equal to and not equal to piecewise scenario, you know, you just plug in the number. And this one's a little bit of a trick anyways, because look at where the piecewise issue is. The issue is occurring at 0. What are they asking us the limit about? They're asking us about the limit at 2. So the issue doesn't even have an influence on this limit question. As we approach 2, we're talking about this piece. 2 is not equal to 0, so we plug it into that first piece. -3 times 2 minus 1, that's -6 minus 1, that is -7. Okay, so don't be thrown off by this equal to, not equal to thing. Zone in on what it's actually asking you about. You're almost always going to plug it into, when it's a limit question, you're going to plug it into the not equal to piece. Okay, that could be the first piece, it could be the second piece. All these have been the first piece, but they may flip it on the exam. Don't get thrown off by that. Okay, so take a minute to look at 17 through 20. Do those on your worksheet, and then come back to the video. We'll look at some more quote-unquote problem functions. Okay, so what if we've got something like this? Here's our function, or here's our limit question. The limit as x approaches 9 of x minus 9 over the square root of x minus 3. So I told you limit, try plugging it in first. See what happens. Hopefully you can see what's going to happen. We've got 9 minus 9, and we have the square root of 9 minus 3. So we've got 0 on the top. Notice that square root is just over the x. So the square root of 9 is 3. 3 minus 3 is 0. We've got that indeterminate form again, 0 over 0. Anytime 0 over 0 comes up, that means you can almost always algebraically manipulate this function to fix the problem. Now, this is not as simple as factoring. We can't factor this. We can't factor with square roots. Okay, I mean, you probably technically can, but we don't teach you those methods. So here's how you're going to handle this instead. We're going to keep the limit notation because we haven't actually evaluated anything. What we're going to do is we are going to multiply top and bottom by the conjugate of that square root expression. So it doesn't matter whether it's on the top or the bottom. In this case, it's on the bottom. It could be on the top causing a problem. But whichever piece has the square root in it is the piece you're going to multiply by the conjugate. Now, you may be looking at that and saying, whoa, this is about to get crazy. It's not actually that bad, okay? Don't freak out yet. I know. Y'all like to freak out when you see problems like this. Do not multiply that top part out yet. Leave it in factored form. I promise you something good is about to happen. Now, you can multiply out the bottom. Oh, my bad. I didn't do the conjugate. You got to change the sign. My bad. Change the sign for the conjugate. So change that back to the square root of x plus 3. All right, so on the bottom, the square root of x times the square root of x is just x, okay? It's like the square root of 2 times the square root of 2. It's 2, all right? Think about this for a second. If we're foiling this out, the outside is positive 3 square roots of x. The inside is minus 3 square roots of x. Those are going to cancel. So that's good. Square root's gone. Last, negative 3 times positive 3 is negative 9. So check out what just happened. We have the exact same factor that we had in the numerator, and guess what? That gets rid of our quote-unquote problem. 9 is no longer an issue for us, so we can, at this point, plug in 9. This is all we've got left, the square root of x plus 3. So the square root of 9 plus 3, the square root of 9 is 3, so 3 plus 3 is 6. Now, I know that doing this on a calculator would have been a heck of a lot faster, and you can do limits on that TI-89. I'm not going to show you how yet, but I'm going to go ahead and tell you, you can do limits on that calculator, but I have seen them ask this question on the AP exam. You got to know how to handle these problem functions without a calculator. You've got to know these algebraic manipulations. Okay? Another kind of popular one here is this big old complex fraction. We've got the limit as x approaches 0 of 1 over negative 3 plus x plus 1/3 over x. If we plugged in 0, you should be able to see the numerator is going to be 0, the denominator is going to be 0. 0 over 0, indeterminate form. Indeterminate form means you can manipulate it and fix the problem. Indeterminate form, you can fix it, you can manipulate it, you can fix the problem. Okay? So, complex fractions, what do? We got to get rid of those little denominators. So again, this is another one of those pre-calc things that hopefully you remember. If not, we're going to go back over it and hopefully remind you of how to do these. Okay, I need a little more space there. All right. So we've got negative 3 plus x and 3 in the denominators. So I think the easiest way to fix these denominators is to go through and multiply each term and see what cancels, and we'll go from there. Okay, don't forget about this term down here. You got to remember that one too. Okay, so here's what we've got. Still got our limit, because we haven't evaluated anything limit-wise. We're just algebraically manipulating right now. Negative 3 plus x cancels in the first one. So we just have 3 plus, don't lose that plus sign right there. The 3's cancel there. We can drop those parentheses because we're just multiplying it by 1. So we've got negative 3 plus x. And then, you know what? I'm not going to multiply anything out down here. I'm going to leave it in factored form because I don't know exactly what's going to happen until I simplify the numerator. So speaking of simplifying the numerator, 3 plus negative 3 is 0. So I still haven't evaluated my limit. Still got that limit notation. As x approaches 0, we've got just x in the numerator. We've got 3x times negative 3 plus x in the denominator. Well, guess what? We can cancel those x's right there. So once again, we've eliminated the problem. I'm gonna take one more step before I actually evaluate this limit, just so you can see how this is fully simplified. This expression right here is the exact same as that complex fraction that I started with. Okay, just in a different form. Now we can plug in the 0. Notice I dropped the limit because I'm plugging in the number. You need to do that. They grade your notation. Now, I haven't seen them do a lot of limit problems on the free response, but you never know. So you need to know when that limit notation disappears. So negative 3 plus 0, negative 3. So we've got negative 1 over 9. Yes, I know the negative was in the denominator, but you can slide the negative sign up into the numerator. We don't leave the negative in the denominator, okay? I will count off of that. Do not leave the negative in the denominator. slide it up to the numerator. Okay, so when you got those square roots, you want to multiply top and bottom by the conjugate. It's going to eliminate your problem. But don't multiply out the other part. Just multiply out the square root times square root part first, because it's going to cancel. That's what gets rid of the problem. With the complex fractions, get rid of the little denominators, fully simplify, and then you can evaluate, and you're good to go. All right, so on your worksheet, go ahead and do 21 through 29 odd. If you want to do all the rest of the problems, knock yourself out. But I typically just ask you to do the odd or the even, and then save the other half of the problems if you need some extra practice later on. Okay, I know these are a little bit lengthy. I don't want you to get bogged down in these, but I do want you to get enough practice. So practice however much you need to on these. Start with 21 through 29, and if you've got some extra time, then you can go back and do the even problems.